All right, happy Tuesday as everybody comes in. So I was sorry to miss last week, but I trust that you were in good hands with Dusty. Like I said, I've really missed last week's lecture, and I'm sorry you didn't get a chemist's overview of atomic orbitals, but we'll get into that later. So I trust y'all did quantum numbers, correct? Yes? And then did you also do electron configuration last week? Briefly? All right, so let's try these two practice problems and see how they go. And we'll just kind of go from there. I'm also trying to get back the huge stack of papers that was supposed to go back to you last week but didn't make their way. And then, so like I said, we're going to be doing review for the whole 2 hours to get ready for your exam on Thursday. And so I'll just say a few things about the exam. So this year we're going to try a new experiment. So I keep trying new permutations of the exam in my quest to write a perfect exam. But it will be open note. But don't get too comfortable because it will be time intensive. And yeah, I think that's all I'll say about it. So let's start with these two questions. Give people about a minute or two, and we'll go over it, and then I'll figure out what we need to cover from last week, if anything. Oh, yeah, sorry. I was trying to show two questions, so I think I can only show one at a time then. So we'll start with that one. All right, so what do we get for this one? Let's vote on it. A, B, some vote for B, C, so maybe B. Any votes for C? And D. Not a lot of voting. Yeah, I saw like a few for B. So this makes me slightly concerned. This is why I don't like missing, but things can't be helped. All right, so what are we looking for? What are these things signifying? So this should be one of those questions that you can answer in less than a minute, right? So if you're already taking too long on this, like it's already over is what I'm trying to say for the exam, right? Like you won't make it through the exam with all your notes if you're struggling. So let's go over, what does this mean for our N here? So energy levels, so then which ones are appropriate if we're looking at rubidium's valence electron? So 5. And then did Dusty go over how to annotate your periodic table for electron configuration? Okay, let's go over that right now because that's like the key and everything falls in line. All right, so periodic table. I would have this on your exam, right? So we start with the 1s. So that's our first energy level like we've been kind of saying, right? So again, helium should maybe be on our s block. And then we have our 2s orbital, right? And if you need to do, right, ns1, ns2, that's good. So 2p1, 2p2, right, going over. So this is np6. So 3s, 3p. Now this is where things get tricky, right? So potassium starts 4s. Now what is scandium? So 3d, right? And so that's a reflection going back to our energy levels. So now this is an aside here. So again, hopefully what you took away last week, right, is we have our energy levels. And so at n equals 1, we have an s orbital is allowed. S. So L equals 0. Energy level 2, now we have an S and a P, right? L is still 0 for our S. And then our P, right, we have 3 possible P orbitals, 1, 2, 3. So 0, -1, +1, right? And so then at our third energy level, n equals 3, that's where we first see those Ds. So then we're at 3D, fill this in. Now 4p, right, for gallium, continue on. So krypton is 4p6. So yes, back to our problem. We're practicing with our valence electron. So our rubidium starts our 5th energy level with our S. Yeah. We're going to talk about that in a second. So like hold your thought. Because yeah, there's 2 different ways that I asked those tricky ones. And so I'm taking a poll right now. So 4D, right, fill those up. Back to 5p. And then just go numerically, right? So we're at 54 for xenon. So 6s for cesium. And then this is where things get weird. Like I said, I don't know what Dusty went over. And so typically with electron configuration, you put the lanthanum here, same with actinium. Even though, not to like get confusing, people say that lutetium and lawrencium are more characteristic D block elements, but again, when filling up the electron configuration, we'll just go in order. So that means, okay, we're at 6s1, 6s2, then lanthanum, right? So this is 3, so 3D, 4D, so lanthanum is 5D1, right? But then we go down to cerium, and this starts 4F1 down here. At least, again, just kind of filling normally. So I know we mentioned exceptions, so we're kind of getting there. Yeah?
4F starts at cerium?
Yeah, if you're just filling kind of normally. So like I said, so if you do the electron configuration of lanthanum, right, it'll say 6s2, 5d1, and then cerium, you might have some discrepancies, right? Well, actually, that one fills like you would expect. So that one, so cerium does fill. So starting with xenon. So xenon, 6s2, 5d1, 4f1. And that is, like I said, what we have determined experimentally. And then, right, just count along. So 4f, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. And again, we won't worry about exceptions quite at this moment, especially for these. So again, filling in order, right, numerically, so 71. And then you go back to hafnium, right, for 72. So then the electron configuration for hafnium, well, try that for a second. So just fill normally. So what does that come out to? Sorry, I'm trying to zoom at the correct level. So then what do we get for our electron configuration of hafnium?
Xenon, 6s2, 4f14, 5.
Excellent. And so again, right, we just filled up normally, so xenon 6s2, then our whole F block, right, 4f14, and then, yeah, back to the D's 1, 2. Excellent. Any questions on that? So that should fill pretty normally, so no surprises there. So just continuing on, so again, label this as 5D. Then thallium goes back to 6P, right? Radon 6P6. And then again, just follow numerically, so 86. 87 is, right, our 7s energy level here. Actinum, like I said, start actinum. So this would be 6D1. Then thorium starts 4F1. Again, just kind of assuming that we're filling normally. So 5F14, 103. Then go back to here. So now we're at, so 3, 4, 5, back to 6D2. And then again, right, filling along, so 7P, etc. there. And actually that does kind of bring up, well, I didn't want to go down too far down the rabbit hole, but I don't know if y'all been keeping up with the news. So they're trying to find element 120 right now. So right, that would be right here. And you can kind of imagine, right, with our talk of energy levels and stability, why they're trying to go for 120 as opposed to 119, right? Because they're trying to fill up that, well, you know, assuming it gets made, that'd probably be the 8s2 that they're trying to fill with element 120. So anyways, we'll see if they make it. I know Japan is kind of leading the race, so they say, and trying to bombard and make those heavier isotopes. But all right, so let's go back to our review question. All right, and so then going back, so okay, we said N was our principal energy level, so that made B and C kind of the correct possible answers. But then what do our L's stand for? So our orbital types, right? So S is 0, P is 1, D is 2, F is 3. And so if we're looking at the valence electron, what does our L have to be for a quantum number? 0. So that's how we ended up with B for our choice there. And then just making sure that the M sub L values are allowed. So again, M sub L, right, goes from negative L to positive L with integer values. And then again, our spins were allowed. So spins are always plus 1/2 or minus 1/2.
So with the orbital type, with the like P shell, is it always equal to 1?
Well, yeah, so it always equals to 1, right? So that means that that's a P shell. But then the M sub L could be anything, right?
Yeah.
So as long as it's a P, then it could be -1, 0, or 1. Does that make sense?
So with the -1, what does it fall under?
For the M sub L?
Yeah.
Well, then it's just one of the P orbitals, right? But then we would have to look at, right, like what, first of all, like what orbital type it is. So like, right, you could have an M sub L of -1, right? But then if our L is 2, well then it's just one of the D orbitals, right? Does that make sense? And we're not like trying to label which one either. They're just kind of like a formality, right? Saying that we have these 3 possible states, just kind of corresponding right to our 3 energy levels. And so as long as it's an allowed value, right, then that's fine. All right, let's see if you can do this one. So I think this one is straightforward. So what's the electron configuration for this? So take a minute or two, and we'll do it. And then actually while you're looking at this one, I'll add a separate question to this as well. So how many unpaired electrons? Trying to zoom in.
On the second one,
Which one?
the second one's 3D8.
Yeah, 3D8 4S2.
Okay.
Okay. So any votes for A? So votes for A. What about B, C, and D? So it should be A. So I think that's, yeah, that's probably the best one. And it fills up regularly. So that one shouldn't be tricky. And so, right, B has too many electrons. C is wrong since we have 3 electrons in the S, so that absolutely can't be it. And then D, this is interesting, right, but it doesn't really like help us with the electronic argument. And then, so let's kind of take the second half of this question. So how many unpaired electrons then does iron have? So 4. So, right, do we all see how to get that? So now we put this in our little orbital diagrams. So our 4s and then our 3d here. So 1, 2, and then 6. So 1, 2, 3, 4, 5, 6. So exactly, leaving you with 4 unpaired electrons. And then this kind of goes into why iron is a magnet or ferromagnetic material, but not the complete story. So, all right, try this one. So same concept. So what do we get for this one? Votes for A, B, C, and D. So yeah, everybody likes C. And so there's a few different ways to do this, right? We could take the electron configuration, so 1s2, 2s2, 2p3. And then, right, these are our valence electrons, so we could fill those in to our orbitals. Oops. So our 2s is filled. And then we have 1, 2, 3. We can also see this from our Lewis dot structure, right? So same information. So 3 unpaired electrons, and then we have 1 lone pair, right? All right, let's try chromium. So see if you can write the electron configuration for chromium. We'll discuss it. All right, so what do we get for this one? Our ground state electron configuration for chromium. Anybody want to go for it? We can do shorthand. Yeah.
I got 4s1
So we'll start with argon, and then you said 4s, 4s1, 3d5. So that looks good. Did everybody get this? And so, okay, so y'all didn't talk about exceptions last week or anything? Okay, so if I have this on the exam, I'll probably phrase it as to like explain for chromium's unusual ground state electron configuration. And so let's go over this, right? And so some people, and I'll kind of call this like filling normally, right? We would expect it to be 4s2, 3d4, right? Well, let's compare. And so this is what I would expect on an exam if I, again, we'll rephrase it since we didn't cover it that well last week. And so we would say, okay, we would expect it to have this electron configuration, but why is it really this? And to show this, right, we want to draw out our orbitals. And so we can kind of draw what we expect, right? So 2 in the S, then 1, 2, 3, 4 in our 3D there. But like we were saying, right, we pay an energy price to have those 2 electrons in the same orbital. And since these are so close in energy, right, it's actually more favorable, again, energetically speaking, to have 1 in the D then, and then 1 in the S, right? So now they're all evenly distributed. Now all the D's get an electron. There's no energy price that we have to pay for pairing. So this is why this is the true electron configuration. Yeah, and then, so to bring up another question, so somebody brought up platinum, and platinum is even like stranger. So that would not be a good one to test over. But again, we might be like, what is platinum's kind of expected versus what is its true? So let's try platinum. So at least attempt it. You know, again, if you did your homework, maybe you already know what the true correct answer is, but we should at least discuss why. All right, so what might we kind of expect just for platinum's electron configuration? So 4F14, and then, sorry, what was the last one?
5D.
So 5D8. And so, right, this looks good. Again, this is just what we kind of expect it to do, filling normally. And then what's kind of weird about this one is, again, I think this was from your review or homework, kind of the actual is xenon, and then it's 6S1, still 4F14, but then 5D9. And this is just like, honestly, even a stranger one, since it doesn't, right? To me, I'm surprised that it didn't go 5D10, right, and have none in 6S. But again, I'm not really sure. So part of right, the unexpectedness here is we have additional shielding now with our 4F14, so that's kind of bringing in confounding factors, but this is what it actually is. And again, you could kind of draw out an explanation, but I wouldn't test you over this on the exam, right? Because that's a little cruel. Let's try copper though. Again, copper is kind of one of those ones you tend to go over, but I may throw it out. So which one is copper's? I think there's been some really extra things on there. All right, so what do we get for copper? So any votes for A, B, C, so nice, and then D, so no one got tricked by D. So yeah, really again, this one, we have B, which is kind of what we expect, and that's why I kind of get nervous about asking this as a multiple choice, because like I said, I don't want to unintentionally lead people astray, right? Because you're just filling up normally. So this might be one of those that I ask, right, as to why is it an exception. And again, right, same concept where you want to show your orbitals and kind of what we expect, right? So this is what we expect, but then again, kind of what its behavior shows us is the 4s actually has 1 electron. Yeah, question?
And that happens because the 3D has less energy than the 4s, right?
Well, they're really close. So yeah, it depends. So right, if you have to pay a price for energy, then it's kind of more happy to throw it into the 3D.
Because it's slightly less energy than the SO4, right?
Well, technically the 4s is slightly lower than the 3D, right? But like I said, once you start talking about other energetics of like pairing them, or again like extra shielding effects, that's where things can get a little weird, right? So like I said, if we're just filling normally, the 4s is always lower, but right, it's not just a simple picture of just which is lower. It's okay, well, do we need to pair them? Is there repulsion, right? Is there shielding? What orbital is it in? And that gets even like more and more complicated if you actually try to.
Would it be more accurate than to say that there's less energy because there is no electron inside of them? And that's why it does that?
Yeah, that's basically it. So right, again, the repulsion from trying to pair two electrons together. And then, right, so the other thing we also have to keep in mind is when we're looking at these, right, this is just like ground state of our metal. And so, again, we're going to take another look at the transition metals like third quarter, and then they're going to do different things, right, based upon their geometry. So once they like lose electrons, right, then their geometry changes and everything changes. So then, right, this isn't like just a picture of everything being degenerate. So their geometry, right, can then influence these energy levels. All right, let's try other review questions. So let's try some more quantum numbers. All right, let's try. Take a minute or two for this one. All right, so do we think A, B, C, or D? So I kind of saw a lot of votes for either A or B. So what are our subshells referring to? Yeah, so S, P, D, F, right? Those are different subshells. So then when we have our N equals 3, right, we have S, P, and D orbitals. So then how many subshells do we have? So 3. But again, don't confuse number of subshells with quantum numbers, right? Because again, they're L quantum numbers are 0, 1, and 2. So I think that's maybe why people were thinking 2 in their head. So just make sure we have those straight. Good. All right, let's try some more. So, okay, so how many orbitals are there in the second energy level? Again, I would kind of think about, can I derive this both pictorially and also with the formula? So how many orbitals do we have in our second energy level? So anybody for A, B, so some votes for B, C, or D. Oh, I don't know why, kind of a bad question. So 4, and so right, you can do the formula. So right, what's the formula for how many orbitals in an energy level? Yeah, so right, n squared. But okay, we have the formula, so that's nice. But again, right, think about what we're saying. Okay, we're at the second energy level, right? So that means what is allowed? Okay, well that means an s and a p orbital is allowed. And we have 1 s orbital and 3 p orbitals. So there is our 4 again. Yeah, that was a mistake in this.
I was like, the orbital's still like.
Yeah,
Okay.
Sorry, I was just trying to make some quick review problems. So then, let's try this one. And again, use both the formula but also your brain. So how many electrons then can occupy our third energy level?
Oh, okay.
All right, so what's the formula slash, what if we work it out? So does anybody know the formula? Yeah, so 2n squared. So, okay, well, what's the answer based off of our formula? So 18. Excellent. But again, right, think about what this means. So, okay, third energy level. So what's allowed? So we have our 3s, our 3p, and again our 3d, right? So our third energy level is the first time we can have our d. And so obviously, right, the S can hold 2 electrons, the P can hold 6, the D can hold 10. And so add those all up, right, for 18 electrons. So either way. Yeah, question?
How do you know the formulas for the energy levels?
I think they were given to you in like one of your labs or something, or again, ideally we should have gone over them last week, which is why I'm kind of hitting them now. But that's why I'm also saying, right, like we have these formulas, but in case we didn't go over them, right, we can always just like brute force them as well. Formulas are nice, right, but it's better to understand how to derive it, honestly. And let's just make sure we can do simple trivia here. So how many electrons in our F subshell? So how many orbitals in our F shell? So A, B, C, or D. Looks like everybody went for C, so again, excellent. So write 7 F orbitals. If I could count, 5, 6, 7. Yeah, 14 total. Excellent. So let's see. Let's try this one. Oops. Oops. All right. So examine this set of these 4 quantum, or the set of 4 quantum numbers. So we don't have our spin, right? But we have our L, M sub L, and M sub S. So which one of those is not allowed? So A, B, C, or D. I don't know why. These got off here with my chart, right? Sorry. So this should be N, L, M sub L, sorry.
It makes way more sense now.
Yeah,
Yeah.
I thought it looked weird too, and then I didn't catch it. Alright, so what do we think for this one? Oops. So which one is not allowed? So how does A look? So A is fine, right? B, no problems with B. C, so what's wrong with C? Excellent. So n minus 1. So yes, we have an unallowed L. And then again on the exam it might say to correct it. So right, you could do 2, 1, 0. All of those would be valid. And then yeah, that's fine. And then D. Nothing wrong with D, so that looks good there.
Is it incorrect because of L equals to 3, it has to have a D structure, or like why
Well,
is it incorrect?
Yeah, because, right, we can do it both mathematically, right? So we have the formula that it says it has to be n minus 1. But yeah, what it's saying is this is our third energy level, but then 3 corresponds to a F orbital, right? And so we don't have the F until the 4 energy level, so that's why it's unallowed. Good. All right. How are we feeling about the quantum numbers? All right, let's try, so let's do, I'll start a new page here. And so now I'm just going to practice some of our other topics. So again, right, some of these you should be able to do relatively quickly. So our photon has a frequency of 6 times 10 to the 14 hertz. What is the energy? So see if you can solve that. All right, let's take some votes here. So A, any votes? B, C, or D? What do we get? I don't really see any votes.
That is not exactly
B, so we got 3.98.
yeah.
All right, that might be true. So what's our formula then? What did we say?
E is equal to HB.
So E is equal to H times our frequency. So then, yeah, we're given frequency. So we just had to multiply it by Planck's constant. So 6.626 times 10 to the negative 34 times our frequency. And so, yeah, about 3.98. So y'all were correct with that. All right, excellent. Let's try. We'll do 2 more and then we'll take our little break here. Okay, again, hopefully there's a correct answer. If not, we'll fix it. So try to do our transition, calculate what the wavelength is in nanometer for 4 to 2 transition. All right, what do we get for this one? So again, right, doesn't matter too much. You just want to focus on your difference between these two. And then, right, if you screw up, just make sure you change it to a positive number. So do we have any votes for A, B, so we all like B, or C? So what do we get for our answers? Let's do this. So 1 over 2 squared, so 4, minus 1 over 4 squared, so 16, times our constant, oops, sorry, 1.097 times 10 to the 7th there, inverse, So yeah, about 486 there for our nanometers. Any questions on that one? All right, let's do one more. So how would we solve this one? So what's the answer to this one? So let's go through them. So any votes for A, B, C, or D? So how do we solve this one? Slash, what should we be thinking, right? Because we still want to test it kind of numerically, right? And so what does our formula tell us? So, okay, I feel like we're kind of down to these two choices, but we should be able to figure it out. So what should we do? What can we plug in?
I don't remember what the constant was, but it's maybe 2.1799 times 10 to the 18.
Yeah, so we have, this is our formula. So 1 over nf squared minus 1 over ni squared. And so we're really just looking for the biggest difference, right, between our final and our initial. So then what do we get for the difference of c? And we can plug this in, right? So you have 1 over 25 minus 1 over 4. All right, so that gives us a 0.21 difference. And then now we test the other one, so write our D. So that's 1 minus 1 over 4 there, right? So which one has a larger difference? So D, right? So then which should be our one with the greatest energy? Right? So it should be D, right? And again, you could finish plugging this in and get the exact energy of the transition, but what the question is really asking is, right, just compare these two numbers, plug in this part of the formula and figure out which has, right, the greatest difference there. And then if you remember, right, we said that, well, we kind of expect there to be the greatest energy difference, right, between the first and the second, and each subsequent one gets smaller and smaller. And so again, the math just backed that up as well. Does that make sense for this one? And so again, like, think about how to approach these questions so that you're not like solving the full energy difference, right? You kind of want to be strategic with your testing strategies. All right, let's take a 10-minute break and then we'll do more practice. And this review should be sharing live on the Blackboard, so you should be able to follow along as well. as we come back from break. So again, ask questions if anything comes up. So let's try one of those percent by mass calculations to find the percent of sulfur in penicillin, and you're given the formula here. So let's start with that one, and then we'll look at multiple choice questions. All right, how's this one coming along here? So kind of walk me through this one. So what do we get for our total mass then of penicillin once we added everything up? So for the mass of penicillin, like talking about the whole mass, so like 12 times 16, and then plus 18, and then 14 times 2. Yeah, what'd you get? Yeah, Max.
338.396.
338? That sounds low to me. So 334. So what do we have? 334, 336? Sorry, I'll add it up as well. 18, 28. 32. So yeah, like 334. So what do we get? So 334 point, so 0.1, so grams per mole. Excellent. And then, so sulfur is about 32 grams. So then 32 divided by 334. So what percentage did we get then? Excellent. So about 9.6, and again, sig fig, so since you weren't given any, wouldn't be too precise on those. Excellent. Easy enough, right? So now let's go over just our ionization energy trends. So look at these carefully. Let me zoom in for y'all. So look at 1 and 2. So which one has the highest one? And again, look at them carefully. And then which one has the lowest first ionization energy?
What is B?
Yeah, B for boron
Oh.
there. So what do we get for this one? So do we think A, B, C, or D? Oh, so I think everybody would be tricked on this one. So everybody seemed to like oxygen, right? And I think you were just going off of the basic trend. So we said, okay, as we go across the periodic table, our ionization energy tends to increase. But what do we remember about nitrogen and oxygen? I know we went over this in lecture. Well, they are diatomic, but that doesn't help us with our first ionization energy. So it doesn't have a full one, but there's something weird, right? And you might want to write the electron. Yeah, so we're kind of getting at it. So something about spin and, yeah, Naya? Yeah, exactly. So, right, let's draw the explanation again. So yes, right, there is a general trend that it increases as we go across, but this is a good exception, and we should know it. So yeah, we'll go over the explanation again. And so again, just rephrasing what Naya told us. So right, we have our nitrogen where we don't have any paired ones, and then versus for oxygen, right, where it has one set of paired electrons in our 2p. And again, like Gabe was trying to tell us, right, we had to pay a price there for the spin, right? So we paired them. So yes, there's a little bit of repulsion there. And so it's happy to eject this one, and then we no longer have to pay that energy price. So yes, oxygen is actually a little lower in energy versus trying to rip one off from the nitrogen, where you have an electron, right, in every p orbital. So it's pretty satisfied in some respect. All right, good. So let's try. So then what do we think about this one? That one should be more straightforward. So which one has the lowest ionization energy? Let's see, votes for A. Oh, people like A. What about B, C, or D? And so again, right, all those are on the same row. Where's my periodic table? So they're all in the same row, so yes, sodium would have the least. Excellent. So let's try another type of problem. Oh, let's do, so we have to determine protons, neutrons, electrons. So what do we get for 56 iron? So see if you can do that. So what do we get for this one? So how many protons?
26.
Yeah, 26. And then how many neutrons then? 30. And then how many electrons? 24. Excellent. All right, let's try maybe a question that we haven't explicitly done, but you can put your problem solving skills together. And so I haven't decided what shape will be on your exam. So here's our sample problem. So we're looking at a cylinder that has a mass of 21 grams, a density of 15.3, and then if the height is 6 centimeters, what is the radius in centimeters? And then I gave some formulas. So this is just density is mass over volume, and then you're given the volume of a cylinder in this case. So see if you can solve this. So again, thinking caps on for this one.
By using this calculator, pi.
Um,
Oh, okay.
so how's our problem going here? Kind of walk me through our steps. Kind of what do we know here? What are we given?
So if we're given density and mass and we're having to find the volume, and then set that volume equal to pi and then radius times the given height,
Excellent. So that was fast. So kind of walk me through. So then you did this first, right? So you said let's solve for the volume. And again, just kind of dimensional analysis, right? Just making sure everything checks out. So then we should have gotten about 1.37, and that's centimeters cubed, right? And so again, that was for our volume, and just kind of rearranging equations. And so like I said, this one's a cylinder, so we were given the volume with the appropriate formula. If on the exam the shape is a box, right, it's just length times width times height, and I believe I provide the formulas. And then again, like she said, so now we can plug this in, so we have the height, and then we're trying to find for our radius. So now just set up the algebra. And so what did you get for your final answer? So I got this answer, 0.27 centimeters roughly. Is that what other people got? Excellent. Thumbs up. So radius is 0.27 centimeters. Oops. So questions on that one? So I would expect to see one like that on the exam. And then there'll be unit converting. So let's practice this unit conversion. So convert 125 centimeters cubed to meter cubed. So what do you have to do for that one? All right, what do we get for this one? And of course, right, we want to set up our conversion factor. So 100 centimeters is in 1 meter, or however you want to express that. But then of course it's cubed, so we want to make sure we cube that. So I'll just kind of set up the work. And again, right, so we want to go from centimeters to meters, so I'll put meters on top, and then 100 centimeters on bottom, and then of course cubing it. And then what do we get for our final answer then? That's what I get. Is that what other people got? So I see some nods, so yes. A little quiet on that side of the room, so that makes sense. So let's do another percent isotopes. I was trying to find. Alright, sorry, I was pulling up some data here. So, looking at ruthenium, is that the one I want to look at? No, that doesn't seem right. Sorry, rubidium here. There we go. Alright, so let's try this one. So rubidium has basically two main isotopes. So one is stable, the other does undergo radiation, but two mainly stable ones. And so the average atomic mass from our periodic table is 85.468. And so the two isotopes that I mentioned, sorry, let me get rubidium's mass here. And so 87 rubidium is the one that's radioactive, but like I said, it's mainly stable, so its exact mass is 86.949118 AMU. And then the other isotope that's stable is rubidium 85, and the mass is 84.9118 AMU. And so given this data, find the percent abundance of those two isotopes. So of 87 rubidium and 85. Let's see if you can solve that. So I think everyone's still kind of working on the algebra. I'll just sketch out the setup. So right, this is the one where we have, okay, well we only have two isotopes, so x plus y has to equal 100%, or 1 if we convert it to a decimal. And then y is 1 minus x. And then, again, it doesn't matter who's x and who's y as long as you keep it straight for the end. So I'll just make 87 rubidium x here. And then just keep as many digits as we were given. And then 1 minus x. And I think most people, again, have this process down, but I just want to make sure that we go over it. And again, remember to distribute. And then algebra, yay, algebra. That equals our average, so 85.468. And so what do we get once we solve this? So you can give me either one. So what's our percent? We'll do 87 rubidium. What do we get for that one? 50.6? Sounds a little off. What did we get? Yeah, that's what I was expecting. So like 27. So you said 27.4, so that should have been for rubidium 87. So about 27.4%. And we could go through it if we need to, but. And then, well, can't do mental math, so 100 minus 27.4. So yeah, about 72.6 then for rubidium 85. Do we have questions on that? So if we need more help with the math, we can always chat about it after class too, of, you know, distributing and all that, but should just be algebra. All right, looking at your tests. So again, just kind of other things that are on there. Right, just like classifying things. So like theory, hypothesis, or law. So kind of maybe doing examples of that. And then there's going to be probably more like unit conversions and all that. And again, right, it's open note, but you can see where it'll be time intensive. Naming. So, right, naming compounds, but just sticking to those simple ones, right? So either our covalent compounds or metals with just one oxidation state. So, and then again, we did protons, neutrons, electrons, so there'll be a bunch of that. Balancing equations, so we didn't practice that right now, but that will be on your test. So writing atomic symbols and interpreting atomic symbols, and then classifying things, so write element versus compound versus a homogeneous versus a heterogeneous mixture. So classifying stuff. Just again, kind of basics on what's a solid, liquid, or gas. And then, right, just kind of those comparisons, like which one will have a higher energy. So I would kind of look at your electromagnetic spectrum, ionization energies. So we already did that. So yeah, periodic trends. You may have to like look at data, right, for ionization energies and figure out, well, what, how many valence electrons it may have. And so we did electron configuration, quantum numbers. So just expect those calculations. Yeah, I think we've pretty much kind of gone over everything. So yeah, open notes, you'll have all of Thursday, so about 2 hours to do the exam. And I do expect it to be, like I said, time intensive and difficult, but that's supposed to be the course. So. Again, just study, be familiar, right, so you can kind of work through the problems quickly, and I think you'll be in good shape. Otherwise, again, if you're trying to do too much studying and hunting during the exam, I wouldn't expect you to be successful. And so with that, right, like kind of plan for success, I would have your periodic table with like your key cheat sheet things, right? Maybe annotate your book with the formulas, or like if you have a weak section, you know, sticky note it so you're like, okay, I'm going to go to this if it comes up on the exam, right? Set yourself up for success so that you have your formulas kind of ready to go, right? So you're not like super hunting everywhere. Maybe have examples. And then you should have gotten all your papers back from me. If you didn't, come see me. I think I have a few like no-name papers. So especially if it's not in the grade book and you turned it in, definitely come see me. But otherwise, it should have found its way back.
We will be in lab that day, right?
Yeah, and then so we have lab this week, so I will see Tuesday people today for lab, and then otherwise I will see you Thursday for the exam and lab. And then everything should be posted. All right. Any questions, or I'll stop the stream?
Are we ever gonna have a lab exam?
Yeah, we'll have it at the end. So I think it's on the syllabus that we have a lab exam.
Gotcha.
So yeah, the stuff that's in like the exam, that was in the, like the review, that's kind of more labby or trivial. Sorry, you won't be tested over necessarily. But yeah, you may see it in lab later. But.
Thank you.